Doctor Herbert. Sí, adelante.
Thank you. My thanks to Professor Nall and the organizers for this meeting. I thought the sessions this morning were very informative, and I learned a lot from many of my colleagues. Today I'll speak about some specific opportunities and challenges in early breast cancer detection. We won't be able to cover everything, we have a short time, but I'll highlight some interesting opportunities and point out some challenges. As you've heard, the opportunity to screen patients may be done in balancing those at greatest risk. Although we think of things such as perhaps family history, exposure to radiation, other risk factors, many people think about the genetic risk as the major driver of risk. Unfortunately, the most common genetic risk factors tend to slightly increase our risk of breast cancer. And those genetic factors that elevate our risk dramatically are relatively uncommon, as shown here in the example where BRCA or the new PALB2 gene are associated with increased risk. They're relatively uncommon. Both the BRCA and PALB2 are associated with DNA repair mechanisms, and we can understand perhaps how the inability to repair DNA ultimately leads to a high risk of breast cancer as well as other cancers. And in fact, these risks, particularly in the North American and European populations, have been well characterized. And in fact, for breast cancer by the age of 50, breast cancer by the age of 70, secondary breast cancers and ovarian cancer, compared to the general population, those with BRCA mutations are obviously extremely high risk. One of the challenges we face, though, is that the ethnic populations that are studied probably are underrepresented in North American studies. For example, the women's health study that's quite widely known as the nurses study from the United States. But a very small percentage of nurses at the time that study was initiated were Hispanic. Although Hispanic now make up a significant part of the population, they're underrepresented in these large population-based studies. Other estimates, as you heard from a really beautiful talk from Susan Love, is that the Hispanic population has a significant increase in the rate of BRCA1, more so than we have expected, and perhaps it's related to the founder mutation in the Aztecs, or perhaps the Jewish migration from Spain for a variety of reasons. And in addition to these other prominent genes, there's a search for other genes. Again, this is a Manhattan plot showing a variety of genes associated with the chromosome in which elevation and risk have been identified. There are dozens to scores of these. Again, how we're incorporating them in our risk models will emerge. Again, I was really pleased to see the high quality work being done here because the specific genes associated with risk in the population here may be different than what's being reported in the literature in the U.S. Let's move on to breast cancer screening technologies. One of the things I like to point out is that our understanding of breast cancer have been really dramatically changed in the past 15 to 20 years due to improved understanding of the genetic and biochemical changes in breast cancer cells. Nonetheless, our screening strategies remain relatively derivative of techniques established approximately 100 years ago, which is the shadow cast by radiographic energies. Again, conventional, now improving to digital mammographic technologies, but still the fundamental basis of detection is anatomic change, whereas our understanding of breast cancer is much more sophisticated. So one of the things that have been explored, significant investments have been made into finding circulating markers for breast cancer. For example, our common markers such as proteins or other macromolecules in the blood, indicators of breast cancer, and many have been reported. Usually they turn out to be not specific enough to really be informative and have never been widely adopted. There was early promise in identifying circulating tumor cells in the blood, because in early stage breast cancer we actually found a surprising number of circulating tumor cells or disseminated tumor cells in bone marrow. Again, we found that these are usually not present in sufficient quantity until cancer is more advanced. And I think that an interesting opportunity now is the opportunity to interrogate blood for circulating DNA and RNA. And that's been a promising approach, not only for different sequences, but perhaps methylation patterns in circulating DNA and RNA. I would say the jury is still out. Other strategies have involved using more direct assessment of the malignant epithelial population. For example, in this anatomical description of the breast, we see that many of the ducts are associated with potential for malignant transformation within them, and in the pre-malignant to increasingly malignant stages, luminal integrity is maintained. Is it possible that ductal lavage or nipple aspirates would provide sufficient information to make screening this way informative and perhaps more precise? I think work done by many, including Sue Love, have demonstrated the utility and the potential for this, but it's not widely adopted at this point. So we're left with mammography, and in the U.S. There's an acceptance that mammography and mammographic screening are the gold standard for screening for breast cancer. Recent recommendations have suggested that screening begin at the age of 50. And what's interesting is that if we look at population-based numbers, we definitely get an increase in the screening mammography rates, now approximately 70 to 75% of the U.S. population, and a very high increase in the amount of non-invasive carcinoma of the breast. But many are perturbed or somewhat disappointed that the rate of invasive carcinoma, and in fact mortality of breast cancer, has not been dramatically reduced by the implementation of mammography. And if you recall the data from cervical cancer, the screening for cervical cancer reduced not only incidence but mortality of invasive cervical cancer by over 80%. And that's not what we've seen even with widespread adoption of a screening mammography. So let me point out, again, some of the challenges we face, as you heard earlier, with, I think, a very beautiful demonstration of the heterogeneity among the populations in Mexico. This is a map of the SEER data, and we recognize that there are higher death rates associated with late-stage diagnosis, as you heard from Felicia earlier. Actually, for those of you who know the SEER data, it actually doesn't represent the entire United States. There are different registries. Some states aren't registered, but you can see Louisiana has a very significant population of very advanced breast cancer. And we are using technologies such as geospatial mapping to map at the parish level, or these are regions, the size of counties, to look at the the incidence of advanced stage breast cancer, and the location, the physical location of breast cancer diagnostic facilities. And as you might imagine, when there's differences in the rates of late-stage breast cancer, there turns out to be differences in the location and the accessibility of mammographic services. In fact, if you begin to map physical accessibility, the driving distance to mammographic facilities actually is directly correlated with the risk of having a late-stage diagnosis. And this turned out to be quite interesting because many people began to think about breast cancer services as a population-based number. For so many women, we need so many services, but we may have to think about the urban versus rural distribution of these services and make sure that accessibility is just as important as physical distance or numbers per individual in the population. Well, let me switch gears one more time to a conceptual framework of early detection. And this is a slide I borrowed from a think tank called the Era of Hope meeting, sponsored by the National Breast Cancer Coalition. And Don Barry, who's a very famous statistician, epidemiologist, thinker, developed this slide that talked about breast cancer starting from 0 malignant cells to a doubling, where now you have a logarithmic increase in the number of tumor cells that exist, and this is associated with non-detectable tumor to microgram, milligram, gram, and kilogram of tumor burden. Obviously, this is very late stage and usually associated with death. Now, what we're aware of is that the clinical detection of breast cancer usually occurs at the 1 gram level. About a gram of tumor cells can be physically detected by a variety of studies. And we were hoping, and we all assume, that mammography increases the lead time for early diagnosis. But what is apparent is that the number of doublings that occurs after a tumor is mammographically detected before it is then clinically detected is only 3 or 4 doublings. So rather than detecting breast cancer at this very early stage, which I think many people assumed that mammography was early detection, it really goes from 30 doublings to 27 doublings. And I show this is an early picture of Madame Curie, which uses, again, the technology we're employing today, which is radiographic imaging. So one of the concepts that's emerging is the idea that the genetic and molecular hallmarks of cancer are oncogenic signaling or biochemical pathways that are activated within cancer cells, and this activation occurs at the very beginning of malignancy transformation, and it's not dependent on the size or number of tumor cells, but it's dependent on the fact that the cells are truly malignant. And the idea is, in fact, that oncogenic signaling associated with metastatic potential and lethality will actually occur before mammographic detection. And all of us who've taken care of patients in the U.S. with breast cancer recognize that about a third of patients, even with a mammogram, will have metastatic disease at that point in the lymph nodes and potentially beyond. So the question scientifically is, can we actually visualize this oncogenic signaling prior to mammographic detection? And so I'll spend the last 3 minutes just telling you about some research where we're recognizing that oncogenic signaling requires what we call chaperones, almost shock absorbers, if you will, of the signaling molecules. And these chaperone proteins actually are ATP-dependent mechanisms where they take on a configuration based on the binding of ATP. And in fact, we can make probes to these ATP binding sites. These ATP binding sites can then be used to detect the earliest, we think, signals of breast cancer. So here's some animal data again, to reflect the wide breadth of science discussed in this conference today. These are animals that have in situ carcinomas, non-palpable. We had to shave their tummies so we can see their breasts, and you can see under the microscope the types of non-invasive breast cancer lesions that are present. And if we take these cancer cells, rather than seeing 10 million or 100 million cells, which we can detect by mammography, we are now being able to detect 10,000 cells, 30,000 cells, 100,000 cells by having probes that are fluorescent, that are producing reflections of near-infrared light, non-radioactive signal that goes in, and light is emitted at a different wavelength. So not only can we detect DCIS, if we look at very small implantable tumors in these mice, this is just some recent experience with the near-infrared probes. These mice have breast cancers, they're palpable, but you can see that once we put the probe in, they become extremely bright red. If we look at mice that use a non-specific probe, these mice also have experimental breast cancers, but again, very non-specific binding, very, very low levels of detection. So I show you these types of data because there's a large segment of scientists focusing on these non-invasive methods. These studies will support the first in-human studies that will be done this year. We hope and expect to utilize these types of technologies and extend them to all parts of the world because the technologies don't require a cyclotron or a massive nuclear energy. These are very user-friendly, non-toxic probes, and they're detected by near-infrared cameras, very commonly things that detect our blood oxygen content when we're in the dentist's office or in the doctor's office for a minor procedure. So detecting breast cancer in young women, there's no question it's going to be a critical element to all the plans that we're looking at to control the incidence and mortality of breast cancer in populations around the world. I think Sulav's description of the incidence of women under the age of 50 being a global problem, I think we completely agree and think of the opportunities as a collegial opportunity to work together. It'll require a better understanding of early non-invasive breast cancers, and we think that there's probably a subset of early non-invasive breast cancers that may have a different natural history. They may in fact be indolent, and our ability to manage them may be different than what we traditionally have done. And we think that there's no question there are solutions to detect the earliest changes in breast cancer, not relying simply on anatomic changes. Again, these involve detecting genetic and biochemical changes in breast cancer cells. Thanks very much for the opportunity, and I'll be happy to entertain any questions as we get back to the